Hi, welcome to the second video about the flow, immersed flow. Let me rephrase that. Let's try and find the flow rate of the fluid through a orifice pipe, a pipe fitted with an orifice plate that's immersed in a river with a free stream velocity U infinity and pressure P infinity. That's a static pressure, by the way. Okay, so what we have done in the last video, we have actually concluded that the pressure at this point, let's say for a completely blocked system, this is the dynamic pressure here, and this is actually the static pressure P infinity. And take note that the dynamic pressure equals to P infinity plus half density of the fluid times free stream velocity of the fluid squared. That's the dynamic pressure. And since we have derived that, now let's take a look and see what happens when we actually open up a small hole. Now you can imagine again, well, in this very extreme case where the whole pipe is actually blocked off, you can imagine the fluid's actually like just flowing around, and this guy's trying to squeeze here, or this guy's trying to squeeze here, or some of them in the middle, you kind of just stop. Alright, I'm not going to draw everything, but you can imagine the fluid is just trying to diverge its way around the pipe. As you go to the back, you might see some turbulence here. Alright, you have some turbulence, and yeah, there may be some drag actually exerted on this pipe, pipe-like system. So imagine, let's imagine we start opening a bit of the hole here. You can imagine some fluid actually starts to flow through, and the pressure here isn't as great. It won't be the stagnation pressure anymore. So maybe we'll have a pressure between, the pressure here will be somewhere between the stagnation pressure and the free stream pressure. Now, of course, as you start opening the orifice plate up, as you open it bigger and bigger, it will become more like a no obstruction case. Alright? No obstruction case where the fluid just flows through without any hindrance, and the pressure here is just P infinity. But you can imagine as you close the orifice plate, or make the area of the orifice plate smaller and smaller, the pressure here will increase until it reaches the dynamic pressure. So you can kind of guess the pressure here will be somewhere between the two extreme cases. You can be between the free stream pressure and the dynamic pressure. We just don't know what. But we kind of know, this is somehow related to the area of the orifice plate, and that will also affect the flow rate, because the faster the flow rate is in this pipe, the lower the pressure will be over here. Alright, so let's draw that again. And this, whatever happens in the orifice plate is the second part of what we want to understand, how we want to understand this problem. Before that, let's take a look at the back of the pipe. And in the very extreme case, again, we may have some kind of an eddy current or some kind of turbulence. I don't know how, but see, as there's fluid being introduced, it starts going here. What it naturally wants to do is just to follow the fluid here. Let's say this is a very, very small opening, and is not so much that this eddy current actually gets pushed back or disappears. This guy will actually want to follow this fluid, this turbulence here, because this velocity is going this way. This guy will want to go this way as well. Call it peer pressure or whatever it is, but the fluid inside the pipe will want to follow the turbulence outside. Okay, and that's a very rudimentary or basic kind of a guess based on this eddy currents or this turbulence. The fluid in here will tend to want to follow the direction of that turbulence, but it'll still go out. Alright, so sooner or later we will still have a pressure here, P infinity. And how do we know the pressure over here? Alright, we can actually do a very similar analysis on this volume over here, just like we did in the last video. Over here we will have P infinity again, and here we assume we are symmetrical again. So if this box here, these eddy currents are not moving, you have to assume that here the pressure is P infinity. So for one thing, you can see that no matter whether there's an orifice plate here or not, we see that the pressure outside here will be P infinity, or the free stream pressure here. So that's one thing good, because we know that this is actually fixed. The only thing changing is the pressure here. And the other thing is that since we have a pressure drop from here to here, once we know that pressure drop, we can actually find out that the fluid flow rate in this pipe. Now question is, this is, let's say, P X. We don't know what this X is. No? I'm sorry, that's English, but never mind. This is Px and this is P infinity, and we say this Px is somewhere in between P0 and P infinity, which is the stagnation pressure and static pressure. We don't know what. So, but we do know the pressure drop across the orifice plate is somehow related to flow rate. How do we now find this flow rate? And that was our original problem in the first place. But to do that, we need to find out how the pressure actually drops. Alright, so our next step is to derive some equations for flow across an orifice plate. So for now, we just ignore whatever's happening over here, whatever's happening outside the pipe. We just zoom in on the pipe itself. Alright, let's say we have some fluid with a velocity here. It's trying to squeeze into this orifice plate, so these guys will converge, and suddenly it has to expand and slow down. So we kind of need to take note of what's going on here. So let's just break it down step by step. Now take note, here we have a certain pressure Px. Okay, certain pressure Px over here, and we have pressure P infinity here. Alright, we don't know what these are, but let's just take a look at the flows first to help us better understand what's going on. Alright, so first thing first, you have these streamlines going in here, and these streamlines are starting to converge as they come into the orifice plate. And take note, this is actually a sharp orifice plate. So due to the momentum of the fluid, the streamlines will actually converge even more a little bit after the orifice plate into what we call the vena contractor, which is over here. Since we are given an area AC, which is, oh, not AC, sorry, A orifice, and this is AC, and this vena contracted area, A vena contractor, or we just call it AVC. This AVC is actually about 0.63 times of A orifice. Okay, so this is just experimentally determined. You don't have to really memorize it or try and derive some equation. It's just found out due to, okay, people have tested it before, so just take it as that. Alright, so let's just take a look at this flow diagrams here. You see the streamlines actually are quite identifiable up to this point, and then after this point they kind of like just go chaotic. You don't really know what happens, so just put a question mark there. But at the end of the day, the flow profile is again re-established, and obviously, as discussed earlier, there will be a pressure drop from here to here. Alright, now we want to derive an expression for that pressure drop. So let's just consider this first control volume here, before the pressure actually drops. So we have a laminar flow, a laminar kind of a flow, or a flow where it is steady, incompressible, what else? No shear, neglect any head loss. So at the end of the day, we just want to apply Bernoulli's equation. So we don't confuse ourselves, let's name this place VC, and we name this area C. So Bernoulli's equation that will be P over rho plus GZ plus V squared by 2 equals a constant. Of course, that only holds under these assumptions. Now this relates to the pressure flow work in the system, P over rho, or P times the specific volume of the fluid. This relates to the gravitational potential energy, and this relates to the kinetic energy. Now let's simplify our equation first. We don't have we are assuming that the flow is really horizontal, so there's no change in height. We can just cancel these terms here. P over rho plus V squared by 2, there should be an average V, equals constant. Alright, so let's place in our subscripts. PC plus PC over rho, which is the density of the fluid, we assume is constant, and it's VC squared over 2 equals to PAC, or VC, sorry, the vena contractor, pressure the vena contractor over rho plus V of the vena contractor, the velocity at the vena contractor. So this should be VC here. We bold it so you can see it properly. This is our first equation. Sorry, it's a bit ugly. Let's just simplify that equation a bit. make it a little neater so that you guys can see a bit better, guys and ladies and gentlemen. Yes. Right, now we have a Bernoulli's equation. We just stop here for now. In the next video, we just explain a little more on how we can actually continue with our analysis.